I'm going to take them one at a time. And you notice I have my quadrants drawn up, okay? My quadrants, because this is going to be very helpful when we take into account this information here about the restrictions on theta, okay? So, number one, cos theta is 3 on 5, theta is acute. All right, right away, when I see this, I know I'm in only one of the quadrants. I'm in the first quadrant, okay? So what I do is I tick this and I ignore the rest of the diagram, okay? So maybe you're like, wow, what a waste. Okay, so really what I could have done, when I read this, I only really needed to draw the first quadrant, okay? But anyhow, it's there nonetheless. Cos theta is 3 on 5, okay? So remembering that, I mean, this only has to be rough because just for the sake of illustration, but to make it roughly, like, at least vaguely to scale, okay? I can see that this is going to be my 3, and this is going to be my 5, right? Because if theta is there, then I've got adjacent on hypotenuse. Adjacent on hypotenuse. Okay with that? So you can see 5 along there. You'll notice, by the way, this is not the unit circle anymore, is it? Okay, it's a circle of radius 5, okay? But because the unit circle and all other circles are similar, that's why we use, all the ratios are the same, okay? No matter the size of the circle. Now we use Pythagoras. This is the Pythagorean triad, so this number, of course, is 4. And I believe, if my memory serves correctly, they want sine and tan. That's all they want. So from this, you literally read off the diagram. Sine theta is opposite on hypotenuse. Tan theta is opposite on adjacent. I'll just take this moment to notice the fact that if we consider this line here going upwards, if we considered its equation, if I said y equals something, right? It's going to be, well, all straight lines are mx plus b, right? mx plus b. What's the b? What does b stand for? B is the y-intercept, which in this case is 0. So it's just going to be y equals something x, right? And m, of course, is the gradient, which is rise over run. Rise over run. Now, I could write 4 over 3 because those are the numbers. But it would be more interesting for me to write, it's just tan. The gradient of a straight line is just, and it always is, tan of whatever angle you're hitting the axis at. We'll deal with that in more depth later, but I just sort of point it out because it's a simple enough question that you're not confused by the rest of it. Tuck that away for later. Let's have a go at this one, okay? Rehearse with me again. I see this information, and what's the first thing I do?
Draw a triangle.
The first thing I do is I got to think about where I draw my triangle, and that's based on the fact that theta is obtuse. So which quadrant am I in?
Second.
Number 2. Great. Tick that, and I ignore the rest. Now, because this is a bit trickier with the negative, right, there are going to be some things here which I want you to watch carefully for. So put your pens down for a second. The triangle is going to be on this side, going off in the same direction. Okay. Now, I drew my scale really badly. I'm going to try that again. It's
We get it.
no, I'm going to do it better. Just because OCD, you know. Get over it. There you go. Okay, that's a little bit better. Now, I've got my right angle there. Now, we are used to writing theta in the corner here next to the origin, right? But I cannot possibly write theta here. Can anyone tell me why theta can't be there? Because theta is obtuse. Very, very good. I'm in a triangle, right? Where is theta really? Yeah, Minsu. Yeah, good. Remember, on the unit circle or on circles, we start measuring from over here, and we go anti-clockwise. That's your obtuse angle. So that's the real theta, okay? But when we're looking at this triangle and doing the ratios and that kind of thing, this angle in here is the angle related to theta, right? So if this was like 150, okay, the related angle would be 30.
Wake up.
I'm awake. Excellent. Okay, good. So, it's a minor thing, but I think it's helpful to show you understand what's really going on. Because this is kind of like theta, but not really, I put it as a theta with brackets around it. Okay, then I am working in this triangle, but that angle there is not the real theta because of what I know about it. Okay. All right, now, in a similar way, right, I have tan, so this is which two sides? Which sides am I looking at? Opposite and adjacent, right? So I could write this as 5 over 12 because all lengths are positive, right? But as you can see, because I'm in the second quadrant, right, This is not really 12, is it? It's actually minus 12. I'm going to the left, right? Now, this does indicate the length. So just like here, I'm going to put a kind of, it's really negative, okay? So minus 5 over 12, perhaps is not the most accurate way to say it. It's really 5 over minus 12, because I'm in the second quadrant, okay? But anyhow, there you go. That's going to be very useful for me in a second when I work out sine and sec. Oops. Okay, so I could say, all right, I've got sine over here, and that's opposite on hypotenuse, right? So 5, 12, hypotenuse is 13. Okay, so I could think, oh, I'm in the second quadrant, so sine must be positive, so it must be 5 over 13, right? That's fine, okay? But having noticed that these numbers have the signs attached to them, I can just say it's 5 on 13. Like, I don't have to worry about which quadrant I'm in. I've labeled the signs already, okay? When I go to sec, right? Sec is 1 on cos, right? So what's cos? Which two sides am I looking at? Adjacent and hypotenuse. Now I see the adjacent side is really a negative length, right? So this should be 1 over adjacent on hypotenuse, which of course is minus 13 over 12, right? So you could say, oh, I'm in the second quadrant, A, S, T, C, cos is not positive, it's negative. Or alternatively, you could just do the signs right from the beginning, and then you can just read off the numbers, which I kind of prefer. Okay.
Could you just draw a triangle and then turn the sides according to like what quadrant?
I would encourage you as much as possible, like I said, like I used to do that actually because it's faster, okay? However, I find it more error prone. I find it more error prone because I get confused about which signs are which, especially when I'm like going over here where they're both negative, or over here and I'm like, which one's negative again? I just find it so much easier. I'm like, look, there's the axes. This is going to the left. It's clearly negative, right? So I don't think it's a huge time saving, and I think it helps clarify what's going on.
It also like clarifies with the inverse, like the cosecants and the secs, which
Yeah.
one is negative.
Yeah, that's exactly right. So, and it's much harder to remember them because we don't work with them very much. But obviously they match the signs of their reciprocals, but this makes it really obvious. Sorry?
Do you have to write it like that? Like one
You mean this pit
cos
here?
A?
No, I was doing that to clarify to you guys which ratio we
Can
were
you just look
interested
at
in.
it in your head?
Yeah, you can. But again, anytime, like just generally speaking, can I just do this in my head? The answer to that depends on two things. Number one, does that process, like demonstrating that process, is that an important part of demonstrating you understand what's going on? Are reciprocal functions really what's being assessed here? No. Really what's going on is, can you draw this triangle correctly and interpret signs properly? Right? That's not the focus. So if this wasn't here, this would lose no marks. Okay? So firstly, is it required demonstrated understanding? Firstly. Secondly, are you going to get it right? Like if you're like me, I'm kind of suspicious of the fact that, am I going to flip it right around the right way properly the first time? Possibly not. So I just write it down. Again, it's not a huge time cost. And when you're in an exam and you are adding more chance of errors because you're rushing all that kind of thing, I just think you might as well. Okay.